Okay, so I am going to share my screen. I want you to, the goal is basically, these are skills that you should already know from Magna Advanced Algebra, but they will be on the summer assignment test. So just making sure that you have a good handle on them. And then we will be working in groups on these skills tomorrow in class. So you need to watch the video and copy down what you don't understand for sure so that you increase your understanding and be ready to contribute to your groups to answer similar questions tomorrow. Okay, so first we're going to look at this polynomial. Couple things about this polynomial. I can tell you that it is odd because the end behavior is down on the left and up on the right. So it's odd and positive because of the end behavior. And the important points that I'll need for these 5 questions are the maximum points, the minimum points. Maximum points relate to turning points. And then also the x-intercepts. I need to know those as well. So for the first 3 questions, those are about the x-intercepts. There are 5 x-intercepts. There's one here, there's one here, there's one here, there's one here, and there's one here. Okay, so there's 5 x-intercepts. The first 3 questions are related to those. If it's not on an integer, then you just do your best estimate and just make sure you continue to use those same values in other related questions. Okay, and then for notation, if we are listing some numbers, we want to use set notation, which is the braces. So that's what I'm going to do. I'm going to list all the x-intercepts because the x-intercepts are where y is equal to 0. So that's what that's asking. Tell me where y is equal to 0, which means points on the x-axis. And again, there are 5. So this was a little bit to the left of -4. So I'm going to call that -4.2. If you said -4.1 or -4.3, I mean, as long as it's close, it would be fine. This one is at -2. I have one at 1, 3. And then this one was between 4 and 5. I'm going to call it 4.6. Okay, so again, braces are for listing, and there were 5 x-intercepts to list. The next question is asking for where y is less than 0. So if it's equal to 0 when the curve is on the x-axis, then it would be less than 0 where it was below the x-axis. So there are sections. There's a section here below the x-axis, a section here, and another section here. There are 3 sections where this curve is below the x-axis. So we use interval notation because there are intervals where the graph is below the x-axis. So that's parentheses and brackets. So we're going from left to right. The first section where the curve is below the x-axis is from -infinity to the first x-intercept, which I already said I was going to use -4.2. Because it's just less than 0, I would use parentheses. That means the x-intercept's not included. But if that were less than or equal to, that would be a bracket because that means I would include the x-intercepts. Okay. The next section where the curve is below the x-axis is from this x-intercept to this x-intercept, which is from -2 to 1. And the third section where it's below is from 3 to 4.6. So then the next question is, where is the curve above the x-axis? So there are 1, 2, 3 sections where this curve is above the x-axis. The first section is between the first 2 x-intercepts. Again, I'm going to use parentheses because it just says greater than, not greater than or equal to. If it said greater than or equal to, I would include the x-intercepts, which means I would use brackets. The second section where it's above is between these 2 x-intercepts, 1 and 3. And then the last section is from that last x-intercept, which I said was 4.6, and then it goes to infinity. Okay, so those are the questions that use x-intercepts for this curve. The next 2 questions are going to use the turning points, okay? So the increasing intervals and the increasing and the decreasing intervals, those are also sections. So I'm also going to use interval notation, but it's going to be from the left to right, from turn to turn. So I'm no longer using x-intercepts. So this section is increasing because as x gets bigger, so does y. And the way that I would write that interval is from negative infinity, since it's coming from an arrow on the left, up to the first x coordinate there of that turn, which is -3. You always use parentheses for increasing and decreasing intervals because once I'm at that turning point, I'm neither increasing nor decreasing. So if you would use a bracket, you would be saying that once you're at that exact point, you are doing something either increasing or decreasing, and that's not the case. Okay. Then I have a decreasing section. So that is from the x of this turn to the x of the next turn. So that would be from -3 to -1. Then I have another increasing section. Again, it's from the turns and the x coordinates of the turns, so -1 to 2. Then a decreasing, x of the turn to x of the turn. And it finally ends with an increase, and that would be from the x coordinate of the last turn to infinity. Okay, and then the last point, okay, I think I made a mistake here. No, 2 to 4. I think I made a mistake on my other page. Okay, so the last part for here is relative max and relative mins. Again, we're using the turning points. We're not using the x-intercepts. And there's a certain way you have to state your relative max and relative mins. The format is important. Do not just give me an ordered pair. I will not count it right. Okay, it has to be in the right format. Okay, non-negotiable. So the maximums, you have maximum turns and minimum turns. This should just either be the top of the hill or the bottom of the valley. So every turn is either a relative max or relative min. So going from left to right, the first turn would be considered a relative max. Use the ordered pair, but I'm going to say 2 at x equals -3. You can use the at symbol, that's fine, but it needs to be stated in this way. Again, if you just give me the ordered pair, I'm not going to count it. Then the next turn, that's a relative minimum. And so again, I want to state it the y coordinate at the x coordinate. Then I have another maximum, that would be 1 at x equals 2. And the last turn is another minimum, -1 at x equals 4. Okay. And you have to alternate, like it would have to alternate from relative max to relative min as you go through from left to right on the polynomial. All right, the next section is related to a piecewise function. If there are no arrows on the piecewise function, then you would assume that they are just endpoints. So the assumption here, even if it's not there, would just be that these are 2 endpoints because there's no arrows. And if there was an open dot, that should be drawn in there as well. So if there's no other indication, assume endpoints. So the domain, remember, is the set of x's that occurs in a certain function. And so you want to go from the leftmost x to the rightmost x, and then you have to remember whether you are going to use brackets or parentheses because you're using an interval again. So this graph goes from the left, it goes from this point to this point. So from left to right, the smallest x is -3, and the largest x is +3. And because we are assuming that those are endpoints, then we would use brackets to include those x values. The range is the set of all y's that are defined for a certain function. So then you go from the lowest to the highest, and we're using the y value. So this is the lowest point, and this has a y value of -3. And then the highest point is right here, and it has a y value of 1. So it will go from the lowest of -3 to the highest of 1. And again, we would use brackets. We don't have any indication that those points are not included. And the roots are x-intercepts. So x-intercepts, it would be the same up here as where we said f of x equals to 0. So we have a point here, and then the endpoint there. So our roots, again, remember when you list numbers, you use the braces, that's set notation, and we have a root of 1 and then of 3. So the roots are the same as x-intercepts, which means y equals 0, which means we're listing the x values. Okay, you should know how to write a piecewise function. There's more than one right answer. Some people might use fewer pieces by using things other than lines. For example, you could incorporate some absolute value functions here and write this piecewise function in fewer pieces, but I'm just going to stick to lines because that's most often what I see for my students. So I'm going to go from left to right. So I'm going to start with this piece. Okay, this is a sloped line. If I start from here, the slope is rise over run, rise over run. The slope is just 1. And then if I kept going, if I kept from the endpoint going up 1, right 1, up 1, right 1, up 1, right 1, it would have a y-intercept of 0. So that's the identity function. So that's just y equals x. But that doesn't keep going. If it was just y equals x, it would be a line that you would see go from corner to corner. And that obviously didn't happen. So that's where you have a restricted domain. So the x values should start at this x value of -3, and it's only going to go to an x value of -1. Now notice the inequality symbols I used. I've included the point -3, and I've chosen not to include -1. I'll explain more about that in just a second. The next section, that's just a little horizontal piece. And the way we write horizontal lines is y equals some y value. And the y value here would be where y is -1. So y equals -1. And that section goes from an x value of -1 to an x value of 0. So the x's go from -1 to 0. And so it's a choice that you make. See how both of these restricted domains includes a value of -1? Well, to be a function, you can't have any overlapping x values. So you have to choose one to be open and one to be closed. It doesn't matter which one you choose. So I just try and kind of get in a rhythm. So I'll do like closed, open, and then here I'll do closed, open, because I'm going to have an overlap with 0 as well. My next section right here, this little linear piece, this also has a slope of 1 from here, up 1, right 1, up 1, right 1, but the y-intercept would be -1. So the slope is 1, the y-intercept is -1, and this piece goes from the x value of 0 to the x value of 2. And again, where I have this overlapping x value for the restricting domain, you want to make sure you make one open and one closed. And my pattern was just closed, open, so I'll make this closed. And then the last piece I have, this is the first piece that's got a negative slope. If you go from here to here, it's down 1, right 1. That makes a negative slope of -1. And then you have to figure out if this was extended, where would the y-intercept be? So you can just sort of ghost plot it. If you keep going up 1, left 1, up 1, left 1, you can see that it would have a y-intercept of 3. But you also have 2 ordered pairs that make up that piece, and you should be able to write the equation of a line anytime you have the slope and 1 point or 2 points. So that's a skill you should still know how to do. The y-intercept, though, if that kept going, would be +3, but we're only going to have that piece go from an x value of 2 to an x value of 3. Okay, again, where I've got this overlap, I'm just going to follow my pattern and do open and then close down here. And then when you get to the end, that is a closed dot, so I want to close that as well. Okay, so on to the next section, which is going to be completing the square. All right, so that involves quadratic functions. So the directions, write in graphing form by completing the square, and then sketch the graph, and then also solve. There's 2 things we can do with completing the square. We can solve, or we can put it in graphing form, vertex form. And so we want to be able to do both of those things. All right, so we're going to start with just getting it in graphing form by completing the square. So if we're graphing, then we need that f of x or that y. So we're going to just leave that there. But the process for completing the square, the steps are basically the same whether you're solving or you are try to put it in graphing form. So I'm gonna change that to y because it's just easier to write. And our first step is to move the constant to the other side. That constant is 11. So if I move it to the other side, it's going to be negative 11, and leave room to complete the square on both sides. All right, so move the constant to the other side and then leave room on both sides for completing the square. So our goal is to make this a perfect square trinomial. The way we do that is we look at the coefficient on x, that's called the linear coefficient. We take half of it and square it. Don't care about the sign because you're going to square it. It means the result's always positive. So half of 12 is 6. 6 squared is 36. If you add it to one side, make sure you balance it on the other side. This is a perfect square trinomial. So that means it factors into a binomial squared. It's always going to be x, the sign from the middle term, and the square root of the number you just added. And then over here on the left, I have y plus 25. Okay, so I'm almost ready to have it in graphing form. I just have to isolate y by subtracting the 25. And it's in graphing form. That's called vertex form. I need a, h, and k. And so you can tell from the quadratic that you were given in standard form, a is the coefficient on the squared term, and that's 1. So I already knew that. I just didn't know the vertex, and now I do. The vertex is the opposite of the number added or subtracted with x. So that would be positive 6. And then k is the number added or subtracted onto the end, and you would not change the sign. That would be negative 25. And then again, a is the coefficient on x squared or right after the equal sign, and it's not there, so we assume it's 1. All right, so let's go ahead and graph that. I went ahead and made a grid. Let's see, I'm trying to set this up just to speed the video up. So just a quick reminder for graphing, the vertex is 6, negative 25. So 1, 2, 3, 4, 5, 6. And then I went ahead because this was so far down and drew that. And then since the a value is 1, we use a 1a, 3a, 5a pattern. You can always use a table of values. It goes over 1, up 1 because a is 1. And then over 1 and up 3 times a. So then it'd be over 1 and up 3. And then you can keep going, over 1 and up 5. And then it would be over 1 and up 7, over 1 and up 9. And you can continue however long you want till you're happy with your graph. But plot the vertex, over 1, up 1 for 1a, over 1, up 3 times a, over 1, up 5 times a. Then it would be over 1, up 7 times a, 9 times a, etc. Okay, so there's your parabola. Arrows on the end. All right, and then what about if we just wanted to solve this? Solving means you're finding the x-intercepts. So basically, if you're solving and you're finding x-intercepts, then that means y is 0. So you've already got the work that you need, but basically we're going to take this step right here. We've already completed the perfect square trinomial and combined our constants over here. But if you're solving, that means y is 0. So we could put a 0 there, and it's just 25 equals x minus 6 squared. And then you can take the square root of both sides. Remember, anytime you're solving and you take the square root of both sides of an equation, you use plus or minus. So then you would add 6 to both sides. Don't leave your answer like that. That's 6 plus 5 and 6 minus 5. So you have 2 x-intercepts, 1 and 11. So if I went back over here to my graph, I would know that if I continued this parabola, it would cross the x-axis at 1 and then 11. And I'm not going to draw that in, but that's what you're finding when you solve. Okay, now the second example makes it a little bit harder because the a value is 4. Remember, the a value is the coefficient on the quadratic term, and that's 4. So we've got a little more to pay attention to. I'm going to start the same way I did before. I want the y, and then I want to move the constant to the same side as the y. So I'm going to add 1. I'm going to leave room to complete the square. I'm going to have the quadratic term, and then I want the linear term on the same side as the quadratic term. So I'm going to move that over there and then leave room to complete the square. Okay, so I'm setting it up the same way I did here. I've got y and the constant with leaving room to complete the square, the quadratic term, the linear term, and leaving room to complete the square. Same thing I did over there, just a little more movement. Now, if a is not 1, you have to factor a away from these two terms. So I'm going to factor the 4 away from x squared and the negative 8x. Okay, if you redistributed, tap what you started with. Now I'm going to complete the square. Look at the linear coefficient. Half of 2 is 1, 1 squared is 1. Now here's something you got to pay attention to. Normally I would just add 1 to the other side, but that's not really a 1, just like that's not really an x squared. It's really 4x squared. It's not really a negative 2x. It's really a negative 8x. So that's not really a 1. It's really a 4. So you have to add a 4 over here. Then I can combine my constants on the left, and I can factor my perfect square trinomial on the right. It would be x, the sign from the middle term, the square root of that perfect square. All right, and then to get it in graphing form, I just need to isolate the y. So this graph will have a vertex of +1, -5, with an a value of 4. So let's look at that graph. Okay, so the vertex is 1, -5, and then a value of 4. So we're going to use still 1a, 3a, 5a, except a is a little bigger now. So 1a would be over 1 and up 4, because that's what a is. So the next move would be over 1 and up 3 times a, and 3 times a is 12. So I have to go over 1 and up 12. Over 1, up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I have to do that on the same side. Parabolas are symmetric, so I have to count again. I definitely like to work smarter, not harder, whenever possible. Okay, so that has a bigger a value, so it's a narrower graph than the other one that had an a value of 1. All right, let's go back to the solving part. Okay, I'm going to take it from here. Remember that if you're solving, it's an x-intercept, so y would become 0. So I want to solve from there. And then I'm going to solve for x. So I'm going to divide by 4. And then I'm going to take the square root of both sides. That means plus or minus. I can't take the square root of 5, but I can take square root of 4. Don't forget the plus or minus. This one, the best I can do is say x equals, and I'm going to add this 1. And think about your answers if you're using the quadratic formula. When I add the 1, it's really the best form to put it in front of the plus or minus. So you have 2 x-intercepts, 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2. So if you wanted to put that in your braces, you could just write it like that. So there are 2 x-intercepts. They are real, but they are irrational, which means they're just not nice, neat points. These x-intercepts aren't something that I could just read off the graph. There would be like yucky decimals if I were to type them into a calculator. Okay, last section, solving log equations. So you have to know your log properties. This is just a reminder how to go from log form to exponential form, how to condense and expand. These are the condensed sides these are the expanded sides equaling the condensed sides. So 2 logs added, condensed to 1 log through multiplication, 2 logs subtracted, condensed to 1 log with division. And it's considered expanded if you have a coefficient on your log and you can condense it by making that coefficient be an exponent. Okay. Other things to keep in mind that when you have a log, the base of the log has to be positive, and the number next to the log has to be positive. And also, you can't have the base of the log cannot be 1, because when you write it in exponential form, it would be 1 to some power, which is always 1. So that doesn't work either. Okay, so first one, whenever you have an equation with just a single log, your strategy is to write it in exponential form. So that means go from this form to this form. So I'm going to take the base of the log, I'm going to write it to the 5th power, and it's equal to 5x plus 7. 2 to the 5th equals 5x 7, just like here, b to the x equals a right over here. And then I'm just going to solve that equation. 2 to the 5th is 32. Subtract the 7, divide by 5, and I get 5 equals x. You can have extraneous solutions with log equations because of these things right here. So you just want to make sure if x equals 5, it's not going to break any rules and it wouldn't make the number next to the log be negative. So it's all good. All right, for the next one, if you have more than one log on either side of the equation, you have to condense it to one log. So I've got 2 logs over here, so I'm going to use this property right here to condense it to 1 log. And this says that 2 logs added, I'm going to condense using multiplication. So this is what it is that I'm going to multiply. So it's going to be log base 4. I'm going to multiply the x and the x minus 12. So that's going to become x squared minus 12x. And then didn't do anything to the right-hand side. Now I have an equation with a single log, which is what I started with. So same strategy, write this log in exponential form using this format. So it's 4 cubed equals x squared minus 12x. 4 cubed is 64. And this is a quadratic equation. So to solve a quadratic equation, generally, your first strategy would be to set it equal to 0 and try and factor it. So if I set this equal to 0, I'd subtract that 64. Okay, easy to factor here. 2 numbers that multiply to give you 64 are negative 64 and add to give you negative 12 are negative 16 and positive 4. And so when you set each factor equal to 0, you would get x equals 16 and x equals negative 4. 16 is good. It doesn't give you a negative number next to either of your logs. But the negative 4 is no good because it would give you log base 4 of negative 4 and log base 4 of negative 16. So that's extraneous. I only have one answer there. And the last one, 2 logs on the left. I'm only allowed 1, so I'm going to use this property to condense. 2 logs subtracted, condensed to 1 log with division. This is what I'm going to divide. So log base 2 of x plus 1 divided by x minus 4. Again, now I have a log with 1, or an equation with 1 log, so I'm going to write it in exponential form, which would be 2 cubed equals x plus 1 over x minus 4. Want to multiply both sides by the denominator so that it will cross cancel. 2 cubed is 8, so this is going to be 8x minus 32 equals x plus 1, and then I'm just going to continue to solve that equation. So when I subtract the x from both sides, I'm going to have 7x. If I add the 32, I'm going to have 33, and x equals 33/7. There would be no problem plugging either that into either of these logs. Obviously, if you add something to one, it's going to be positive. And this is bigger than 4. Okay, 7 goes into 33 more than 4 times. It doesn't quite go in 5, but it's a bigger number than 4. So you would still end up with a positive number here. So that also is not extraneous. Okay, so make sure you understand all of these topics and concepts and be prepared to contribute to some breakout rooms tomorrow to work on these topics.